In this video, I'm going to introduce you to reaction rates, which basically is change in concentration divided by time, but there's different ways to calculate it and different reaction formulas and balance equations that we need to consider when we're doing this. So this image here shows so-called elephant's toothpaste. It's when a violent reaction takes place that's very quick, and a lot of oxygen gas is released to produce a foam. Generally, this is done with hydrogen peroxide that's colored with food coloring and maybe even has some detergent added, so it makes more of a bubbly mess. And you could imagine putting this on an elephant's toothbrush, so they call it elephant's toothpaste. All right, and so this is the decomposition of hydrogen peroxide. Now, when hydrogen peroxide decomposes, you can see that the concentration is quite high. Here it's given an arbitrary value of 1.00, and it goes down over time. This is a very slow reaction. You can see how after 6 hours there's about 0.4, and then 12 hours there's about 0.2 molar, and 18 hours so on, okay? And what you'll notice, first of all, is that in this chemical reaction we have a couple different products and we have one reactant, okay? So the idea here is that we use concentration in brackets, all right? This is critical that you understand this. We use this for kinetics, equilibrium, buffers, and everything else in the rest of the class, okay? So whenever you see H2O2 in brackets, that means molarity of hydrogen peroxide or moles per liter of hydrogen peroxide, okay? We use that abbreviation a lot. Now, the idea here is that the rate is equal to the change in concentration divided by change in time, and that's basically the tangent to this curve, okay? This curve is constantly changing, the rate is constantly changing, but if you take the tangent, okay, or the slope at a particular point of that curve, you're gonna get the rate, okay? And the rate slows down as the reactants are used up. All right, let's talk about relative rates. Now, rate is change in concentration per time, and the concentration we use here is molarity, which has capital M as our abbreviation, okay? Now, obviously, reactants decrease over time and products increase over time. And so what you're gonna see is that change occurs differentially. That means if you have a reaction A plus 2B going to C, imagine you have a big pile of sand, okay, representing A, and then you have a pile that's twice as big of gravel that's represented by B, okay? And you're using that to make cement or something. And you're gonna see that the pile of gravel, the B, right, is gonna go down twice as fast because you need 2 shovelfuls of the gravel, or B, per 1 shovelful of the sand, okay? So A and B are both reactants and they disappear at different rates, okay? B is going away twice as fast as A. But the reaction as a whole has one reaction rate, and I'll talk about how you express this. All right? So let's take a look at a complicated reaction. A plus B goes to C plus D, and then we have coefficients of A, B, C, D, all right? Now what you have here is the rate is equal to the change in concentration divided by change in time. Remember, those triangles means change, and brackets A mean concentration of A, and small t means time, all right? And what you need to do is use the coefficients of your balanced chemical equation to get the correct term here in terms of math, okay? So you divide by A, or you divide by B, or you divide by C, or you divide by D. Now, if you look closely, you can see A and B have negative signs there. Why is there a negative sign? Well, it's simply because the change in concentration, which is the final concentration minus the initial concentration, is going to be a negative number. And you can't have a negative rate. That doesn't mean anything in terms of chemistry. So you put a minus sign there, so the two negatives cancel out, and you always have a positive rate. It doesn't matter how you express the rate in terms of A, B, C, or D. All of these numbers will be one single number. It's called the rate of the chemical reaction. Here's an example. Write the rate in terms of ammonia for this. Looks like a combustion reaction, okay? We have ammonia combining with oxygen to produce water molecules and nitrogen, okay? So first, you want to write this general kind of thing. The rate is equal to the change in concentration divided by change in time. We're talking about ammonia, so let's plug that in there. We also have a negative sign because we're talking about a reactant. So don't forget the minus sign for reactants. And then, of course, there's a balance, a coefficient of 4 in the balanced chemical equation, so we need to divide by 4t, okay, to normalize the reaction in a sense, okay? So that is the rate in terms of ammonia and time, okay? Let's do nitrogen. Nitrogen's a product on the right. Okay, so again, start with the general term here. Rate is equal to change in concentration divided by change in time. Nitrogen concentration, plug in there with the brackets, okay? And then it has a coefficient of 2 highlighted in orange here, so you need to divide that by 2, or 1/2, okay? So what we have here is no negative sign because we have products, okay? Products don't require that minus sign in the rate kind of expression here, okay? All right, here are a couple other concept questions. Which product will form faster? First, please remember that products are on the right-hand side of this equation, okay? And we have 6 water molecules being formed and only 2 nitrogen molecules. So obviously it's going to be water because you're forming more of them per event. We'll call it a reaction event, okay? So water forms faster, okay? Even though there's one rate for the whole chemical equation, actually water molecules are formed faster in this chemical reaction. Which reactant will be consumed faster, okay? So again, remember reactants are on the left, and we look at the coefficients. We have a 4 for ammonia and a 3 for O2. So once again, with my analogy with sand and gravel, if you're gonna need 4 scoops of ammonia per 3 scoops of oxygen, you can see how the ammonia is going to be utilized faster or consumed faster in this chemical reaction. All right? Let's switch gears here and talk about instantaneous rate, okay? Now again, if we have a chemical reaction, A going to B, we know that the rate is equal to the change in concentration of A divided by small a divided by the change in time, okay? And we find the change in concentration of A from the final concentration minus the initial concentration. So again, use your calculator to calculate that result. And then the change in time is the final time minus the initial time, or just the stopwatch time if you're starting from time equals 0 and you have a stopwatch, okay? So let's do an example of this. We have a question. After 3.4 seconds, the concentration of ammonia decreased from 0.0150 molar to 0.0147 molar. What is the reaction rate? So ammonia there is the second molecule on the left, or the middle molecule drawn here, and we need 4 ammonia molecules for this chemical reaction to occur. The product here is called Schweitzer's reagent, and it was once used to purify cellulose. Now it's used as an analytical tool to just quantify the amount of cellulose. This is a deep blue color. All right, so let's go ahead and do the math. So first of all, what we want to do is calculate the change in ammonia concentration. Remember that the triangle means change, and it's always final minus initial. And you'll notice here that the final concentration is lower. It's 0.0147, and the initial concentration is higher. So that's why you have a negative number here, and I've highlighted it in orange so we can make sure to use it, okay? So I'll place that off to the side here so we can use that in the future. Next, what we want to do is calculate the change in time. And there's no initial time and final time, there's just a time. So it's just 3.4 seconds, okay? And I'll set that off to the side. Now what we want to do is write the rate. And this is going to depend on the coefficients, right, in our balanced chemical reaction. Just throw it out there. So we have a negative sign because we're talking about reactants, and it's the change in concentration of ammonia. We write that in brackets, divided by 4 times the change in time. And then we just kind of just plug and chug things into the formula here. We just plug negative 0.0003 molar in place of the concentration, and we divide by 4, divide by 3.4. And after I do that all on my calculator, note how the 2 negative signs there cancel out, kind of, and you get a positive rate. Rate should always be positive. Rates always have units of molarity per second, okay? I could write molarity and then a fraction bar and then write S on the very bottom, but it's going to squish my slides and just make things smaller. So oftentimes you see people write it to the right. Seconds to the -1 means 1/seconds. All right. If you need more practice, please take a look at my channel. I recommend OpenStax problems 4 and 5 for your consideration. Please check the link below for those videos. Thanks for watching. Please like, please subscribe. Have a great day, everybody.